He's very this session be named after Professor Harun Rashid. I did not have the privilege of meeting him. I joined in 1973 the University of Islamabad. He left in 1971. But my senior colleagues spoke very highly of him. He was one of the top people at what was then a very good department of physics. Since that time, he has moved on. He's spent a lot of his time here at the University of Dhaka, but apart from that, he was a visiting scientist at the Imperial College in London. He was also a visiting professor in Karlsruhe and many times a visitor at the ICTP. He then went to the Center for Particle Theory at the University of Texas and then the University of California. So a very accomplished person, and it is very appropriate that this session has been dedicated to him. Our first speaker today is Professor Zahid Hassan from Princeton University, who has done an enormous amount of work on topological insulators and other topological phenomena in condensed matter physics. So I invite you, Zahid, to begin your lecture.
So you have the remote or?
No, it's okay.
আচ্ছা হ্যাঁ সেটাই বুঝতে পারছি ওইখানে কাজ করতেছি কিন্তু ল্যাপটপে কিছু দেখাচ্ছে না Okay. I'll go to this one. It's not projecting. Okay. So I use this one. Okay, thank you. Thank you all for joining us. Let me first start out thanking the organizers for giving me the opportunity to speak at this wonderful symposium in honor of S.N. Bose. And it's really a great pleasure to be back here. Last time I gave a Bose lecture here about 10 years ago. So it's nice to be back with some new results. And this time, some of the new results will connect more to Bose than to fermions or bosons than fermions. So I think this is exciting. Okay, so let me. Okay. Is this okay? I can turn on one more. Okay, so the main scientific talk is about topological quantum matter. And as you know, the quantum matter is generally broadly divided into made of either bosons or fermions. And so this distinction, you can immediately see how fundamental this is. So I'm going to say a few words first about bosons, then about fermions, and then I'll come back to bosons, okay? So it's really amazing that this such a fundamental thing, how to classify quantum matter, the entire universe is made up of quantum particles. And this fundamental discovery, theoretical discovery, took place in this very place. I'm really thrilled and honored to be speaking here. This is really a historical landmark in physics. So you can see that in the plot below Bose's picture that there are three types of statistics or behavior of particles, behavior of collection of particles physicists talk about. These Bose-Einstein behavior or Maxwell-Boltzmann behavior or Fermi-Dirac behavior. So the Bose-Einstein and Fermi-Dirac, these are the quantum behavior of particles. So for the very broad audience, if you take many quantum particles, put them together at low temperature, the way they behave is described by their statistics. So this is for the very broad audience. So we are talking about how many quantum particles put together behave at low temperature, and if it turns out their spin, some quantum number, if it's an integer, then they follow the Bose-Einstein statistics. And if it is half integer, then they follow the Fermi-Dirac statistics. And immediately we learn in textbooks that at the very low temperature, the ground state, the lowest state of these Bose particles is a Bose condensate. And if the particles are fermion, half integers, the ground state is a Fermi surface. For example, the fact that all these metals or conductors you see, conductors at low temperature, they have Fermi surface. On the other hand, light is a quantum particle. This is a Bose particle. So that at very low, the light particle or photons, they show Bose statistics. So any matter you can think of is made of these fundamental particles, and they have this contrasting behavior. And so half of that, half of the rules that are obeyed by these quantum particles are discovered by Bose. So this is an enormously magnificent fundamental discovery. So you can see that half of the particles are called bosons in the list of fundamental particles, the other half are fermions. So this is already an enormous impact of Bose's work. There is life beyond that. For example, perhaps to the popular crowd, the most important recent discovery about boson is this Higgs bosons that scientists used billions of dollars to search for it. So this is one exotic example of Bose particle. And there are other examples of Bose physics, for example, the Cooper pair bosons. So the Cooper pair bosons they lead to superconductivity. They lead to some sort of condensation type behavior in an interacting setting, but the Cooper pairs are like composite bosons. Another example would be the condensation of neutral atoms, known as the Bose-Einstein condensation. So all these, I gave only three examples. All these three cases have been recognized with major prizes, and this gives you to the broad audience how foundational his work is. Okay, and more. So this is what we learn from the textbooks, right? So let me add my version of it, why I'm here. Anyone of you can give a talk like that what are the fundamental impact in physics of both statistics. So let me share some other point of view, again, for the broad audience, is that, for example, Nobel laureate Lev Landau, thought that he had an index. He made an index of physicists, how to rank physicists, how their contribution or their genius. So in his list, in the Landau list of ranking, he ranked Bose with Schrodinger, Heisenberg, De Broglie, Bohr, Pauli, Dirac, and all these people. So this is amazing. So these are the names that who are the founders or architect of quantum mechanics. They led to the foundation of quantum mechanics. So clearly, Landau thought Bose was one of the key founders of quantum physics. So there's no doubt about that. And Landau is in the 60s or 50s, but is this something from the old age? This is not so. If the impact continues, then you will hear other great scientists of contemporary time, recent times. They will also have their own way of measuring the impact. So I have my own personal encounter in few such cases. For example, I was a student of Steven Weinberg, who shared Nobel Prize with Abdus Salam. He had great ideas. He had great thoughts about Bose and the condensation and its impact, so that I got to learn directly from Steve. And also my senior colleagues like Phil Anderson or John Hoffield. So this is in a dinner where we're celebrating David Gross and Frank Wilczek's Nobel Prize on QCD. So we're discussing, sometimes, especially Phil Anderson, Phil apparently thought that when I asked him why Bose was never recognized with a major prize, Phil thought I would know better. So he threw back the question to me, why do you think that Bose never won the prize? So it's interesting. So this is how much, I'm saying that how much his impact has grown from Landau to Anderson to Weinberg, all these people in recent time, even in my age. So that means not only the impact of Bose's work is growing, it's also the fact that he really deserved a major international recognition is a contemporary thought as well. But it's unfortunate he's gone. But we all know, I mean, this is not new, that it's what matters is not the recognition, the very fact that you made something solid that had impact, right? There's nothing more satisfying than that. And so that Bose already achieved that, and he had that sense of security, internal security in his own mind. So he never sought after those things. And I think this is a different way to look at it, that he could be a role model for the rest of the world, that it's not, you don't go for the prize, you go for the real thing, and learn to be satisfied internally that you actually did something real, right? So how many people have done something real and own so many prizes? And it should not, I mean, the prizes don't give you a full measure of your contribution. Think about Mahatma Gandhi, right? Gandhi never won a peace prize, but we think of it as a symbol of peace, a nonviolent movement, right? So it's not only Bose, there are other examples of that. I personally counted at least 10 major mistakes or misses by major international recognition. But these people, they had the real solid understanding of life and what it means to be really contributing to advance humanity. So in all those metrics, all those standards, they have succeeded in all possible ways. So I prefer not to talk about why some prize was not missing, but along that line, I want to conclude this slide by saying that both Phil Anderson and Steve Weinberg, in my own encounters, they told me that, Bose is in the textbook. You learn it in chapter 1. So how can you recognize someone. Many Nobel laureates, their work is not appearing in chapter 1 of quantum mechanics, right? So this is already enormous recognition. So appearing in the textbook is then you're immortalized. Your contribution is there. It's written in stone. So I mean, I just noted 3 such impactful work that are part of the textbook. So now I'll switch gear and talk a little bit about fermions. I was initially interested in bosons, like gauge bosons type of thing, while working on QFT with Steve Weinberg. But later, I became more interested to explore the fermionic world because it looks like the Fermi surfaces can be quite interesting, and especially Fermi surfaces can have topology. So that brings in my interest and the current context. So, so I'm talking about topological effects in quantum systems, quantum many-body systems. They are condensed matter systems. They're described by quantum field theories because there's a mapping between statistical mechanics and quantum field theory. And so topologies can be manifested, quantum topology can be manifested as a macroscopic quantum phenomena, similar to superconductivity or superfluidity. So I'll give you some examples of that, and then I'll come back and ask this question: is it possible that in real, not in the optical lattices, in real materials, is it possible that some Bose condensates can be topological? So this is likely to be possible. So even in topology, the Bose is, I think, coming back. So this is another new emergent direction of his impact. Okay, so since this is kind of like a talk in a very broad audience, I'm not going to go into great depth or details of the topological theories that describe quantum matter or quantum many-body systems. But at least for the students, I wanted to give a list of reviews that you can look up to follow my talk, the depth and details of my talk afterwards. So I would say the first review I noted here, this RMP 2010, this one it introduces topology in condensed matter, both from theory and experimental point of view. So it makes a very clear connection between the real world, the abstract math of topology, how that is manifested in the real experimental world. So if you're experimentalist, this should be a good review to start with. And then the other reviews get more technical in theoretical depth, especially both these last 2 reviews, one by Ed Wheaton and by my other colleague, Duncan Halden. So these two reviews are for if you want to be a theorist, so this would be a good starting point. But if you're interested to explore the connection to experiments, I think first 3 reviews could be the starting point. Okay, so then, as I said, I'm not going to review these concepts in theoretical detail, but what I will try to tell you in this slide is kind of a completely experimentalist way of looking at topological phenomena, at least in the macroscopic world. Okay, so in this slide, it's trying to tell you that if you take a piece of rock, the experimentalists are interested to explore the world, right? The physics started that way. You stumble into a piece of rock and try to figure out what is it, right? And then over the years, we learned that its internal structure is ultimately described by quantum theory of atoms and molecules and crystals and structure. And then more recently, the quantum mechanics, going beyond Schrodinger equation, we added special relativity that gave us Dirac equation, and then the Dirac equation gave us made a way for topological, the Hilbert space topological aspects to be introduced. Okay, so this is the conceptual framework, but okay, why did we need to introduce those ideas? And if I go to the lab and say I'm totally clueless, how can I tell that I grabbed an object that is topological as opposed to something that is not? How do I know, right? So this slide is about that. It's taking the problem totally around, go back to the hunter-gatherer life, the Homo sapiens evolved out of that. How do we, in real life, sense and touch and feel and know that something strange about these materials, that they're topological? It should be possible. So this is the basic foundational aspect of science. So we know that playing with materials, say insulators, so when we have a piece of insulators, a piece of rock, so then we try to run electricity through it. We can try to run it through the surface or through the bulk. And we always find by doing experiments, in fact, chemists were doing those experiments before physicists, and they always find that the surface sometimes can be conducting, bulk can be insulating, but most of the time surface is insulating, bulk is also insulating. But then in the cases where the surface is conducting but the bulk is insulating, this is not a universal case because the surfaces can be cut open in many different ways. If you look at a side surface, you'll see that the side surface is again insulating. So there's no universality between surface conductivity and bulk conductivity. So, but it turns out there are classes of materials, for example, bismuth-based thermoelectrics, where it turns out to be it's impossible to cut open a surface that is not insulating. It's always conducting, and the bulk is always insulating. And that is very strange. Its strangeness becomes even more clear that the surface conduction is also strange, not the fact that it conducts. It's strange in the sense that it looks like if you count electrons, how many electrons, what are the degrees of freedom or the phase space, you find that when that happens, the surface, no matter how you cut open the surface, is always conducting, the bulk is always insulating. Only in those cases, you find that half the electrons are on the surface, compared to other cases when something is always conducting or something is conducting on the surface in the bulk, but there's no universality. Some surfaces are conducting, others are not. So there's a clear experimental distinction that not only the cut surface doesn't depend on geometry or the dangling bond properties or the property of the surface, it's some sort of universal property. Not only that, you also have a phase space thing. It looks like you always have, when that happens, you always have half the electrons compared to other conductors. So this is an experimental signature that something strange about it. Why is this strange about it? So I'm going over this slide. I'm taking a little more time because this slide gives a complete summary of my talk. What is topological quantum matter from an experimental laboratory point of view? Theory, many people, we all know there are many papers and all that. But I still find there's a lack of purely experimental understanding that what is topological in a lab setting, okay? So then what I'm saying is that these insulators have half the degrees of freedom. So it reminds me Bose's factor of 2. There's something strange why there's a factor of 2 missing, right, in Bose's derivation, although it's in a different context. So if you would be doing experiments, you'll find that there's a factor of 2 problem. Why is that? So the other thing is that it's invariant, it's independent of, you have a cubic thing, look at this surface, you cut this surface, you cut this at all possible angles, you get the same result. So you see that something is not depending on the geometry of your setup or of your crystal or your sample. it's kind of some quantity that's independent of geometry. So that you start thinking what you learn in math. What type of properties are independent of geometry? So that mathematicians call that topology, right? So then you might think, oh, maybe this is some sort of topological effect because I change so much geometry and it looks like conductivity is the same, and then always I have the half the degrees of freedom. There's a factor of 2 problem. Where did that problem come from? So the fact that this factor of 2 or this half problem of a half is an invariant of many geometrical variation gives you first indication that something must be topological. But you can immediately see when you look at the crystal structure of these materials, they're all crystallographers worked it out. There's nothing strange and nothing topological in their structure, like Bose set up this X-ray crystallography. If you use Bose's machines, look at these materials, you'll see there's nothing topological structurally. So then you have to conclude that that factor of 2 strangeness must be coming from the electron behavior because the X-rays are sensitive to the total charge of the atom, right? So then that electron behavior is, now you see that the electrons are in a periodic potential in a crystal. So then you see that they are behaving like block waves. I mean, you know the term block waves, or they're wave property. So then you realize that you have to use quantum mechanics. So then all possible combination of these block waves define a Hilbert space, right? So now I give you a simple, quick example. Let's say I put a particle in a spherical well, in a spherical potential well, in a sphere inside a spherical well. Now I ask, if this is a quantum particle, what is its Hilbert space? What are the all possible wave functions? We see that because of the symmetry, all wave functions will be spherical harmonics, except the radial factor, right? And all these spherical harmonics, we know, they're defined by 2 angles, theta and phi, right? So now we see that its entire Hilbert space is basically all possible combination of those angles, because all possible wave functions that the system can take in principle, right? Now you can see that I want to parameterize its Hilbert space. The simplest answer is that way to parameterize is that you have a sphere. On top of a sphere, any point you pick, it's described by 2 angles. So then you pick a specific spherical harmonics that describe its wave function. Now you ask this question, okay, now I know my parameterization of my Hilbert space, which is a sphere. Now we can always ask this question. What if I take this sphere, as we have seen in the last talk, that if I take this sphere and deform it in a way that I turn it into a donut, meaning open a hole through it, it's still describing some parameter space, it's still describing some Hilbert space, although we don't know what physical system it's describing. It's not the particle in a spherical well. So then we can do the reverse problem. We ask this question, now that my Hilbert space has a topological twist, that it has punctured hole through it, now that it's a donut, what does that imply for the physical property of the crystal, of the material? Now I can backtrack that. And then it turns out some of these surface states, this invariant count of the surface states on various surfaces that doesn't depend on thing, it turns out it's related to having its Hilbert space, 1 hole, 2 hole, 3 hole, all sorts of things, right? So this sort of gives you a quantum mechanics level of topological thing we are doing. So that means now it's telling me that I change when I cut open or deform the crystal, I change many geometrical properties, but its Hilbert space still has a hole. So then that half of the electrons are missing or half of the electrons are there, that property I cannot change because it's tied to the fact that its Hilbert space, this abstract parameterized space that I haven't changed, right? So it turns out many of these states kind of like that, except that I use quantum mechanics. So these are large N systems. Large N systems, we know the large N limit of quantum mechanics is quantum field theory. Then it maps onto statistical mechanics and all of that. So that's why they describe condensed matter systems. So that means I'm thinking about a Hilbert space that's at least 10 to the 23 times large, dimensional, right? So then I'm thinking about the topology of the 10 to the 23 dimensional. So this is much more, so condensed matter physicists, sometimes I joke with my students that we work in much more higher dimension, many dimensions than the string theories. They have now come down to 11 dimension, right? So we're doing quantum field theory type of thing in the 10 to the 23 dimensions. So that's basically the idea. Now you can ask this question, okay, so this parameterized Hilbert space can have different types of topology. Then we can ask this question, then the fact that its topology is not destroyed by certain number of deformations, what properties are special that are tied to this? Okay, and so one example we already found in 2 dimensions, that's called the quantum Hall effect. This was discovered in 1980s. You know that in the quantum Hall case, what is protected, what is tied to that Hilbert space topology is the Hall conductivity, sigma xy, conductivity tensor sigma xy. And the sigma xy is precisely quantized. E square over h, or the resistivity. So what you see that it only goes in steps. That is not surprising for a quantum system, because quantum systems has quantum numbers. Jumps happen in quantum, in counts of quanta. But what is surprising, that quantum number of that quantum Hall effect is absolutely enormously precise. It's precise in 1 part in a billion and more than that. So much so that these dirty condensed matter crystals, solid crystals, are used to measure the fine structure constant or Planck's constant, all these things. Now, this is a metrological standard. So when I was not aware, I used to think those fundamental constants of nature were measured by high energy experimental methods, but it turned out those methods have much less precision. So the condensed matter, although these systems are not as clean as high energy atomic systems or high energy particle systems, the precision is much more, orders of magnitude higher. So they are the basis of international standard. Not only that, not only just fundamental constant, for example, the SI unit constant, for example, even kilogram is defined in terms of the Hall constant. So this is amazing. So what is the answer? What is the mystery to this? Mystery is topology, because here those quantities are tied to topology. So they are resistance to non-ideality, meaning the variations of geometrical variations or disorder or fluctuations or other things. So they're like the Platonic numbers, Platonic ideality. So the topological invariants are that clean. So I already gave you some sort of overview why topology is interesting, how this is connected to quantum physics, quantum field theory, how they are realized in solid state quantum system in a piece of rock. Bismuth selenide you can find in a piece of rock in some mines here and there. You can just grab it and realize that it has this property that is the most precise measurement of Planck's constant, right? So you see the Bose and Einstein, they're writing Planck's constant, electric charge, and all sorts of things. So those things are, even up until now, most precise measurement come from topological invariants, the topological things. And this is the experimental consequence of topology, that we found enormously profound, almost sacred holy numbers, that these numbers cannot change. So we take that as a standard of things. Okay, so now let me come to this, what is new about these things. So this was in the quantum Hall in the 80s, and that led to at least 3 Nobel Prizes. So the most recent surprise happened in early 2000, where in the old days, the quantum Hall, and that also led to different types of quantum field theory, like Chern, Simon, Landau, Ginsburg, all sorts of quantum field theory was invented to describe fractional quantum Hall effect. But they all describe similar type of topology. What happened earlier this century is that physicists realize there are new type of topological invariants possible. So I started, my first example is from there. I started with the new one. So what is new about it? I already described what is its behavior. If you go to the lab, do experiments, you find this invariant electronic properties. And this is the first example of topological invariant in higher dimensional condensed matter systems. So before that, it's all 1D or 2D. Before at least this experimental work, there was no example of three-dimensional topology in physics, three-dimensional quantum topology. This is the first example, to be more precise. So how do we now, so this is a simple measurement. How do we do advanced measurement, more precise quantum measurement that clearly nails down those topological invariants that are so godly number, if you like, the holy numbers? They're so precise, so beautiful, so powerful that they're protected. So how do we do that? Here we use, at least, use what is called angle spin resolved, angle resolved photoemission spectroscopy. This is basically the modern version of photoelectric effect that Einstein got his Nobel Prize for, right? So you see, it's not only Bose who was not recognized for his most seminal work. Einstein was also not recognized for his most seminal work, which is relativity. But he managed to get a Nobel Prize by trying to explain experiments. So that experiment was the photoelectric effect, right? So that's something his contemporary understood, and there was experimental proof, and everything was there. So that led to his Nobel Prize, and he never got a prize for. So sometimes people are ahead of their time, and then their peers at the communities fail to recognize that in time. So I'm using the technique that was the reason for giving Einstein a Nobel Prize. So he explained, if you shine photons and kick electrons out, then there is a quantum process. In that process, the parallel component of the electron as a wave and the solid is preserved. Okay, the vertical component is not. So we can use that to explore the quantum states or wave functions of the electrons in the two-dimensional space. The surfaces are two-dimensional, and I'm using photoelectric effect. Let me back up. Using photoelectric effect to map out all the quantum numbers, the energy, momentum, and spin. You can do that all with the photoelectric effect. Okay, so by doing that, basically I'm measuring all the quantum numbers that is to be associated, to be used to define the wave function. Now, if I can measure all possible quantum numbers, that means I am tracking all possible wave functions. That means I'm tracking the entire Hilbert space. So then I can, by imaging that, I can figure out what is its topology. That's the basic idea. And I'm not going to explain all of that, how we do that technically, but conceptually that is what it is. I'll show you some results. So then, based on topological insulators, we figured out if they're protected by something called time reversal symmetry. If you break time reversal symmetry, you can make something called, actually this term, we coined this term, you can make a topological magnet or hedgehog magnet, and where where I'm plotting the quantum numbers that describe the magnet's wave function, energy, momentum, and spin, and it has this hedgehog type structure in momentum space. The real hedgehog is in real space, but I'm talking about a topological magnet behaving like hedgehog if you look at it in momentum space. So this is a signature of this signature of a magnet being topological. Similarly, now you might wonder that topological insulator, now I understand that there is a gap. Electrons cannot enter the bulk because the bulk is insulating, so they are confined to the surface, so they're protected to be two-dimensional. But how can you then have a topological conductor or semi-metal? It turns out It's possible, but in a different way. So this is called topological semi-metal or Fermi arc metal or Weil semi-metal. So their topology is different type. They're not of the same type I talked about here. Here you have Z2 invariance. Here you have Chern, a pair of Chern number and anti-Chern number. So these are called Weil semi-metals. So starting with topological insulators, in 2015, we figured out how to create topological metals or topological conductors that have this Weil property. Weil, again, is named after Hermann Weil, who was also at Princeton. He was a colleague of Princeton who took the Dirac equation and considered what is the possible solution when the mass term is 0. And he found that only in 3D, you can have the chirality as a Lorentz invariant good quantum number, but not in 2D. That's why graphene Dirac fermion is not a Weil fermion. So I was aware from the graphene that graphene can simulate a Dirac fermion, but it cannot give you a Weil fermion of the dimensionality because the chirality in 2D is not Lorentz invariant. But in 3D or higher dimension 5D, it would be a Lorentz invariant quantum number. But that theory is already in quantum field theory textbook that I was introduced to through Steve Weinberg. So that was not surprising. What was surprising that we could make it after 85 years or something. That's because we were working on topological insulators. We knew how to manipulate topological insulators, how to change its topological invariant, realize new stuff, and realize new realization of quantum field theory objects. Similarly, we are working on topological superconductors. So this is my connection to Bose and topology in real materials. So one way to make a topological superconductor, this was proposed by Fu and Kane. Kane is my long-term collaborator in a neighboring institution. He's at UPenn. So if you take a topological insulator surface that I studied exhaustively for maybe 10 years, and attach a superconductor, then your Cooper pairs from the superconductor, Cooper pairs are like composite bosons, they will then try to tunnel into the Dirac fermion states. Now you see that the Cooper pair, its phase space or its Hilbert space, and the Dirac fermion phase space, there's a discontinuity. This is not the same. So it turns out if you try to Cooper pairs try to jump into the topological insulator surface where they encounter a helical Dirac fermion, strange half Dirac fermion, then what happens is that they suddenly have to get rid of half of the Cooper pair. So you realize a half Cooper pair gas because you don't have phase space. And then if you calculate, if you have half Cooper pair gas, if you write down the Hamiltonian and solve its vortex, you find that the vortex state, there's a zero energy state that's like a real solution to the Dirac equation, which is called Majorana. So since it's a real solution to the Dirac equation that you find in a half Cooper pair gas on the surface of a topological insulator, then you ask this question, okay, so now I have a bispinor wave function solution to the Dirac equation. I want it to be real, right? Because only the real solution is Majorana. Now you want to find its antiparticle, you take its complex conjugate. What is the complex conjugate of a real number? It's the same thing. So the Majorana is its own antiparticle. So this is in a trivial sense. People sometimes make fancy out of it, but it basically, you ask real solution to the Dirac equation, and so Majorana is its own antiparticle. So now you see that the topological insulator surface, which realize single Dirac fermion, this is what I realized around 2007 or 8, then immediately I realized that now I have a Dirac equation in a material, in a piece of rock in my hand in my lab. So this is like having a QFT lab. So then the surface of a topological insulator is then just a quantum simulator for all of QFT that I learned as an undergraduate. And you can see that if you split the Dirac fermion in 3D, you get Weil. There's no other way to do that. And then if you impose a real solution, you get Majorana. So all of these follows from topological insulators. And this is kind of like a summary of what I wanted to get across. And then I will show a few slides that are more technical for the technical audience, but this is what I wanted each and everyone to get it. So now I will show you one last thing in this slide, that where is my Bose condensate? Here. So you see, using the photoelectric effect, I can break Cooper pair, but then the photoelectric effect is measuring, before it was broken, the quantum coherence. In other words, it's the condensate peak. So this is my BEC of Cooper pair, and the more coherent the system is, the sharper thing I will get. And this gap is protected. This is superconducting gap. This is my Bose. So in this slide, again, I could not avoid the Bose appears again, finally, right? So even in this slide, Bose you cannot avoid. So you can see its impact in physics. So this is my Bose condensate in a topological superconductor. Okay. Okay. So now, this may surprise some of you because this is not the popular conception, but if you look at the early history of topological matter, which narrated by Charlie Kane, this is now published by AIP, he clearly says that I was doing these experiments even before his theory, and that is true. He has seen our lab evidence that we were actually doing these things before anybody even predicted. Of course, we did not have full understanding because the theory was not there. So basically, we experimentally discovered topological surface state or this topological quantum phenomena before they were theoretically predicted. Okay. So now, again, here it gets a little more technical. I'm now trying to explain one or two things because I don't have a lot of time, so that you get a flavor of it. Maybe, yeah. So let me tell you what are the experimental technical breakthrough we had to achieve to realize all those results. So I want to say one more thing about these results. When I started to teach at Princeton, condensed matter physics, I would enter the class and tell students that the condensed matter physics is about macroscopic world, trying to understand, say, metals, insulators, magnets, superconductors, their symmetry-related variants, phase transition, all of that. And this is what you find in Kittel's book or Ashcroft-Marmin book. So I was telling my students 20 years ago, now you know that in last 20 years, we realized half of the condensed matter physics was totally missing in the textbook. So going back to Weinberg or Anderson's criteria, what gives you a fulfilling scientific life, that your result eventually becomes part of the textbook. So now at least a half dozen condensed matter physics books have been published, and they are now being taught, not only at Princeton, everywhere, where most of these results are part of the textbook. So sometimes I tell, it never happened to me that, I never realized when I went to Princeton that I will be, in next 20 years, I will write half of the textbook of my own field. So this is a lucky moment. And not only that, each of these images, the value of each of this image is a PhD degree. For example, this image was taken by my first PhD student, David Shea. He's now not only a tenured professor at Caltech, last year he became the chair of the physics department at Caltech. And that was the first time I realized that I'm getting old. And my most recent student is on the tenure track at Harvard. So I did not mention their name, but each of these images that now appear in the textbook, standard textbook, they're all established in academia. And I find that what is fulfilling, that they are either at Harvard, Berkeley, or Caltech, they're pursuing this topological physics. So this is how your legacy goes on. When your academic progeny, they continue to thrive in the academia, pursuing the field they learned in your lab, is their fulfillment. It's not some external recognition or anything, that you start to feel that you achieved something, you contributed something, you can sleep well at night, right? So, this is my last slide probably. This is technical. I gave you a list of things, what we achieved technically. For example, we figured out this RPS technique was mostly used or developed to explore superconductors, especially high temperature superconductors, correlated systems. Those people, including my advisor, had no clue how to measure Z2 invariant, 4 of them. So that's what we technically achieved. We showed instrumentally. We also built instruments, how to measure 4 invariants, and how to do bulk boundary correspondence, how to do direct spin momentum locking using RPS, how to measure Chern number without doing quantum Hall transport by doing spectroscopy, how to detect chiral fermion, how to detect chirality of Weil fermions, and how to detect, say, Lorentz violation. The Lorentz symmetry is not sacred or holy for condensed matter. It's holy for particle physics, but in condensed matter, you have emergent Lorentz violation. We figured out how to detect such violation. So I have a long, and then, and then once we have done that, I'll just very quickly browse through the text, not go into details, that our discovery of this thing, this David-Chase Dirac cone, it led to many subfields, like people tried to introduce superconductivity on the Dirac field, do quantum Hall effect, do Chern insulators, do Kondo insulators. Basically, all of condensed matter physics, or almost all of physics, can be done with these topological objects. And then, so as I said, that once I realized that I have a single Dirac fermion on a piece of rock in my hand, in my lab, I have an entire laboratory for quantum field theory, because now Dirac equation is like, now I can do quantum simulation. The rest is how to do materials engineering with this piece of rocks. So as I said, with Dirac equation, by breaking inversion or time reversal symmetry, I can create Weil semimetals, Weil fermions, and by introducing Cooper pairing, I can introduce Majorana fermion, and the Majorana is can be used as a, since it's its own it's an anti-particle, it's like a 2-level system. You can use it as a qubit, topological qubit. So this is what I mentioned, that once you have Dirac fermion, then you get Weil and Majorana naturally out of it. And let me just quickly browse through some of that thing and just show one thing that we recently realized. All of this condensed matter physics, there's a big major criticism. There's a beautiful, absolutely aesthetically great quantum research, but they're always at low temperature, right? So they're not very useful. So this is a criticism from the engineering colleagues. So how do you realize this topological stuff at high temperature or room temperature? So we had some recent success, this paper in Nature, where we showed that you could realize some of this topological stuff even at room temperature, although under UHV. So that means this is our transition to the technology world. So last few years, I'm giving some talks in engineering and technology circles. That's because of this, because now all that low temperature, exotic, fragile quantum physics, now we are trying to bring it up to room temperature, because your iPhone or laptop, you cannot put it in a liquid nitrogen or helium drawer, right? You have to use quantum engineering in room temperature. So that's the thing to have greater impact, the way transistors had greater impact beyond the physics community, right? So we're working along that line. So that is one major direction, but at the same time, I'm going both. This is my last slide. So I'm going in both directions. I'm going deeper into exploring the mysteries of topological quantum physics, but I'm also going in other, so that's in the parallel direction. So I'm also going in the other direction, trying to find realized materials that you could have applications that connect to the engineering communities. So this is my last slide also for students, because I talked about a lot of things just verbally without showing math or data, where to find the stuff I talked about. So I talked about how you go from topological insulators to topological magnets. I talked about how to use wire fermion semimetals and find other things like nodal line magnets, Hopf-link, or knot theory related stuff. And then I talked about, also mentioned this also type of Kagome magnets that you could use to many body physics, superconductors that break exotic symmetries and Majorana modes and all of that. So these 4 direction of research that has emerged recently, last 2-3 years, for students, you can find in this 4 review papers that we published. This turns out to be all in Nature. And these are all 21, 22 papers. So this is my last slide to tell you where to find the stuff. I kind of gave a public speech type of thing. So this is my concluding slide that last 20 years, surprisingly, unexpectedly, we apparently discovered half of condensed matter physics. So that surprised me. I just never expected that will happen when I entered this. Thank you.
Thank you, Zahid. That's a huge body of work that you've done, and I'm sure there are going to be a lot of questions here. We don't have much time because we have 2 other speakers, but let's have some quick questions here. Talat?
Unless some student wants to ask. If a student wants to ask a question, then...
Go ahead.
Okay, so beautiful, as always. And the whole thing is, of course, it has come from all these years of studies, right? And one of the things that plays a dominant role in all of this are the surface states, right? Surface states. So could you comment something about what could be some descriptors of properties of systems that the surface states emerge such that the surface is topologically protected?
Yeah, so it's, I kind of gave a more abstract argument that since we find these surface states or single Dirac cone or half of the electrons compared to, say, graphene or other things, independent of the surface or independent of the material, they're always there. So that tells you something is not changing when other things are being changed. So that's, I suggested that as an early sign of topological protection, that something is not related to the surface itself. So for example, I have say nickel sulfide or sodium chloride. I have various bonds, right? Now I break and open a surface, then there will be some dangling bonds. And the electrons can hop from here to there and create some sort of surface state, right? But then if I cut at 37 degrees, same crystal, then the bonds are different. So I should get it, if you ask a chemist, they'll tell you get a totally different electronic structure. So this is the mystery. How do you always get a same half Dirac cone? Because, so that tells you that it's not related to those local chemistry of the surface. And it must be then related to that entire Hilbert space that's generating, springing out that in all directions. So
Yes.
that's one way to think about it. Yeah.
Thank you so much for this wonderful talk. I have 2 very specific questions for you. You talked about topological superconductors.
Right.
Have you looked at the order parameter, what kind of symmetry those order parameters are?
That's a very good question. And this is a current research. We just got funded. You know, US is now investing billions into quantum research. So a few years ago, there was like a multi-billion-dollar initiative And most of people know why that is so, because China is investing 30 billion, so US's 5 billion is nothing. So, but still, they came up with 5 billion, right? So one of my projects is funded under that. So I'm trying to do, I need more money for that to build a new STM system, is precisely what you are saying. So what we want to do, let me explain the question to the broader audience. So what Professor is saying that I'm measuring topology by doing bulk boundary correspondence. I'm measuring the boundary, sometimes also bulk, Weil fermion in the bulk, or Dirac surface state in the surface. So there's a mathematical correspondence between the two. So then the question is, when I want to explore the topology of a superconductor, I say that you create a vortex. That means vortex is the normal state where inside the vortex, Cooper pairs break apart. They're not Cooper pairing, right? So I have to create a normal and superconducting interface to probe the topological boundary, because it's always at the boundary between trivial and topological, right? Now, this is a good question. For a superconductor, whether it's topological or not, I do not necessarily have to create that bulk boundary thing. It should be encoded in the order parameter itself. For example, the superconductor can have S wave order parameter, D wave order parameter. It tells us about the interaction or weakness of the interaction or strength of the interaction. But the order parameter should also tell us about the topology of the state, because order parameter, by definition, should capture the essence of the ground state. Quantum ground state is entirely, many-body ground state is fixed by this. So what he's asking, Professor Saleh Hassan Naqib, is that if we measure the order parameter of a superconductor and find that it's P plus IP or D plus ID or something, that would be another alternative way to measure topology. And yes, my proposal is now funded, so we are trying to build an instrument to do such a thing by doing this. Let me tell you the experiment quickly, is that I take a candidate topological superconductor, instead of creating Majorana, which is difficult to interpret a lot of the time. Many people tried that, not only us.
The second one is also very simple. As you spoke about Bose-Einstein condensation.
Yeah.
Is there any heat capacity measurement? Because if you find something like lambda transition, that will be a very good.
So here we are doing, it's difficult to do that type of measurement because we are doing that using MB grown film under UHV, and in a very delicate, fragile state where we can only do STM or RPES or some sort of crude electrical measurements to do a thermodynamic contact measurement. Currently, technology is, at least my lab is not there. I think rarely any lab can do that. You have to break the vacuum, take the film out and measure that. It's a difficult thing. But yes, this would give another signature that there is some sort of entropy, change of entropy.
Thank you. Thank you so much.
Thank you, Zahid. There's just one question I am dying to ask. Not from the field.
Yeah.
Topological protection can't be perfect. For example, take the fractional Hall effect.
Yeah.
P over Q, at some point this becomes just ordinary number, you can't even tell whether it's rational.
Yeah.
So at some point that topology is breaking down, that which is responsible for the plateaus. Can you comment on that?
Yeah. So this is also true for my type of topology. I did not talk about quantum Hall type topology. That's the old type of. This is also, but the question is broadly applicable here. Yes. So let's say even go back to the integer quantum Hall, even before that, simpler system, the Chern number quantization, right? Even that is not, that's fragile if you raise temperature too high, right? So it's not protected against large fluctuations. It's protected against limited fluctuation, but it's enormously protected compared to non-topological system. The difference is orders of magnitude. Of course, if you take, you don't have to go to fractional. You just take integer quantum Hall, heat up the sample. There's too much thermal disorder, fluctuation, all of that. The topology is destroyed. So topology is not infinitely protective as long as you do not introduce perturbation or fluctuation in the system that the Hilbert space deformation is not drastic enough to change the topology. So in those cases, in the fractional quantum Hall or interior quantum Hall or in my systems, it's as long as you are not destroying the Hilbert space topology, it's protected. This gives you the major degree of protection, how much jolt, how much disturbance the system can. It's not infinitely robust. It's that robustness is determined by a phase transition driven in the Hilbert space. As long as you don't drive a phase transition, you're fine.
Okay, thank you very much.
Professor Hoodbhoy, I have got a question. The question is, Professor Zahid Hassan, is it exactly true that the half of the particles, half of the universe particles are fermions, and half of the...
This is a metaphorical statement that we classify. I mean, you cannot count how many photons are there, right?
Yeah, yeah,
or how many gluons are there. These are kind of metaphorical linguistic way of saying that there's two types of classification, and this is not a numerical half.
Yeah, exactly.
It's a symbolic, metaphorical half.
Okay, thank you.
I have a question. Thank you, Dr. Zahid Hassan. You delivered your lecture here 9 years ago.
Right.
Bose lecture, I remember you were talking about topological insulators. And at the time, you talked about low temperature. Now you have been...
Yeah, last time I only talked about topological insulators because I don't think I discovered other things.
No, then you have discovered room temperature.
Right.
Right. And this still shows the quantum effects.
Yes.
And now my question is, at high temperature, will it still exhibit quantum effect or behave like a classical insulator?
Yes. In a recent paper, I think 2 years ago, we showed that considering temperature alone, for example, this is what we showed is that was in topological insulators. So it has to do with the gap structure, right? So the topological insulator is insulating in the bulk that makes the surface electron, these Dirac fermions, they're 2D, they're mobile, their mobility is only in the surface, right? They cannot enter because there's an energy barrier. That energy barrier is the bulk band gap, right? Now, let's say band gap is small, say 5 millivolt, and thermal fluctuation is 25 millivolt. If you raise temperature, the electrons on the surface have enough thermal energy to enter the bulk. So they're not going to retain their topological protection. Now the Hilbert space is gone. Now the protection is gone, right? So what I'm trying to say is that what we did, we figured out how to increase the gap. So the gap is, say, 50 millivolts. Now I raise temperature on the surface of the bulk. Now the surface electrons have energy of 25 millivolts. They cannot enter the bulk because the barrier is still 50 millivolts. They haven't crossed. So it's about materials design to keep the Dirac fermions 2D only on the surface, even if at room temperature, so thermal fluctuating energy is lower than the gap energy, the barrier to enter the energy barrier to enter the bulk. So that is the idea we used, and we succeeded. But there's one caveat that we did that under UHV condition, not on the open condition, ambient condition. So for engineering applications, your laptop or iPhone, you cannot run it under UHV, right? So what we said, that we at least overcome the barrier, the temperature barrier. Yeah, you can run it at room temperature, but you still keep it inside a vacuum chamber. So the next engineering barrier would be how to
keep it open.
Keep it in air. which is not easy. That's again chemistry problem because the air molecules do chemical interactions. And that,
We must move on.
Thank you.
Thank you very much, Zahid. Wonderful talk. Our next speaker is Abhishek Dhar, and he's going to speak about black hole entanglement dynamics. My apologies, this is not about black holes. I thought it was.
Okay. Okay, so first I would like to thank the organizers for inviting me to this very nice conference. Especially, I would like to thank Kamrul for convincing me to come. He has a way of convincing people, I think. It's my first time in Dhaka, and it's really great. And I hope really that there can be more interactions between with people in. India and so on. It's really sad that I mean we're so close and yet the interactions are so rare. Okay, so what I'll talk about is this work on page entanglement. It's kind of motivated by the information loss paradox in black holes. But there's also just pure condensed matter interest. This work is done with a really fantastic postdoc at our institute, ICTS, Madhumita Saha, and my colleague Manas Kulkarni. And just before I came, this paper got accepted in FISREP letters. Okay, so let me start by giving some motivation of why, what led us to looking at this problem. So let me first explain the black hole information loss paradox as I understand it. So as we know, black holes are formed by like there's some star which explodes, and then the matter just because of gravity it gets attracted and they collapse into a very small volume. And from classical physics, basic description of a black hole is that nothing can escape. So this is an image of a real black hole that was made quite recently. But of course, we know that everything should be described by quantum mechanics. So a black hole is in principle a quantum object which can be described by a wave function psi, and that's what I will call a pure state. And what Hawking had this famous calculation in 1975, where he showed that even though it's black, supposed to be nothing can escape, but actually black holes can radiate. And eventually the black hole vanishes and turns into complete like pure radiation. Okay, so now what is the information loss paradox? So initially the black hole is a pure quantum state, and it has the wave function has detailed information of what the star is made of, where the atoms are located, etc. The final state is thermal radiation, and it's in a mixed state. Okay, and the final state just depends on a few parameters such as the mass and the charge and so on of the black hole. Just macroscopic properties of the black hole. All the microscopic information seems to be lost. Okay, so this is kind of the paradox. Okay, so I mean, okay, and so like to quantify this in a mathematically, one sort of key observable is entropy. And what Hawking's calculation in 1975 involved, I mean, so there's like quantum gravity is difficult. So what he did was a semi-classical calculation and showed that the radiation entropy keeps increasing until till the time the black hole actually completely evaporates. Okay, so this means that you are generating a lot of entropy, and even though you started from a pure state which has zero entropy. Okay, so this is one way of looking at the paradox. Now, Page in 1993 did a very famous had a very famous argument, where he basically looked at I mean, so this was a completely static calculation. You just take a quantum system which is in a random mixed state, which is supposed to be a highly entangled. Okay, it's maximally entangled state. And if you look at two subparts, then you can calculate the entanglement of between one part and the other part. And as you increase this size of the subpart, what you can show is that initially the entanglement increases, and then it goes down. Okay. So now what Page argued is that you can think of the black hole and the rest of the universe as one pure system, and then you compute the entanglement between the black hole and the rest of the universe. And as it evaporates, I mean, since the size of the black hole is decreasing, it should initially it increases, but then eventually it should start decreasing. Okay, when like the Hilbert space dimension of the black hole and the environment is the same, at that time it should start decreasing. Okay, so now from Page's argument, it looks like the entropy should decrease, while Hawking's calculation showed it keeps increasing. So this was kind of the one way of looking at the paradox, and demonstrating like this Page curve in a quantum gravity calculation would perhaps resolve this paradox. And so it's recently this has been achieved since this 2019. There have been large number of papers which discuss this, and there's now a quantum gravity calculation which shows that actually the entanglement increases and then decreases exactly as the Page curve predicted. Okay, so perhaps there's no longer any paradox, but still I think there is a lot of discussion, and some people are still not. They have different views on this, which I won't discuss. Okay. Okay, so again, this is like a schematic of what I just said. So here what I'm plotting is the entanglement entropy versus time. as in the process of evaporation of a black hole. So what Page said is that the entropy should increase, and then at some time, which is referred to as the Page time, after this time, so this is the time at which the Hilbert space dimension of the black hole and the universe are roughly the same. Okay, so they have the same number of qubits or whatever. And after this time, it should start decreasing. Okay, and what Hawking showed is that the radiation, if you look at the entropy of the radiation, it keeps increasing. Okay, so this is the paradox, and okay, so now let me come to what we have done. So there's actually very nice discussion in Quantum magazine on this paradox and its recent resolution. Okay, so okay, one other thing that I should mention is that this is a bit different from the other very famous problem of the arrow of time, which is like, I mean, simple to state it in this context of a free expansion of a gas. Okay, so here I have a gas contained in this tube, and I open this valve, and after some time we find that the gas is uniform across these two tubes, right? So now we never see that the reverse thing happening, right? So there's a clear arrow of time. So the sort of, if you like, paradox is that even though the microscopic laws, Newton's laws or laws of quantum mechanics are reversible, but in practice we observe this irreversibility, right? So so the understanding of this irreversibility is because what we observe in the real world is really a coarse-grained view of nature, right? We are not observing the molecules all the time. There are a huge number of molecules. We can't keep track of their microscopic degrees of freedom. What we observe is really things like densities and so on, and they have much less information, right? So, irreversibility arises due to our lack of information, and it's quantified by entropy and the second law of thermodynamics. Okay, because we don't know at the things at a microscopic level, that's why we observe irreversibility. Okay, and of course the fact that there's large numbers, that's important. I mean, so you have what is known as, like, what is the typical thing that happens. The reverse could happen, but it's extremely improbable. Okay, so this kind of things work. Okay. So in contrast, the black holes, what the paradox there involved is more about microscopic irreversibility. Okay, so at a microscopic level, it seems a pure state goes to a mixed state. Okay, so here note that pure state is always remains pure, but still the entropy increases. There's no paradox. Okay. Okay, so now let me just say what we have done. So actually, I mean, I just want to apologize that when I prepared for this talk, I was not really thinking, and it's kind of technical, but I'll try to explain. And if students have any questions, they can ask me at any point, like during my stay. You can just catch me and ask like anything related to this, or yeah, just feel free to ask. Okay, so what the motivation of this present work is to just look at a very simple, like, statistical physics model where you can see basically this page dynamics. Okay, and the model that we choose is kind of motivated by early work by these people Calabresi and Cardy, where they look at entanglement of free fermions. Okay, and like what happens when a free fermionic gas is quenched into some state and then it evolves. So there's a lot of earlier work, and there's actually two very recent papers which is very close to what we have done. I mean, when we, as we were preparing our draft, we saw these two papers, which also try to understand the information paradox using this kind of a toy model. Okay, and our main results are, first of all, you can, like, we write a microscopic Hamiltonian, and you can compute the entanglement entropy, which Page had computed. And then you can try to understand this, how the entanglement evolves with time. Okay, so you can do a completely microscopic calculation, which is based on you have to do it numerically. On the other hand, you can also do a semi-classical calculation based on something called generalized hydrodynamics. And hydrodynamics is like taking a coarse-grained view of nature. And what we find is, one of the remarkable things we find is that this microscopic and the hydrodynamic picture agree extremely well. Okay. So this, of course, we know, I mean, in general, there are two ways of looking at matter. Like in air in this room, you can look at a microscopic level, or you can just write Navier-Stokes equation for the air. And we know that Navier-Stokes already captures a lot of things about the system. Okay, but here, I mean, what is surprising is that hydrodynamics captures something which is supposed to be extremely quantum, right? Entanglement is one of the most signatures of the quantumness in a system. Okay, so I want to make it clear that we don't include gravity. There are no interactions, so it's a very special model. So it shouldn't be we are really not trying to explain real black holes. But we believe that our model captures some important aspects. So one of the things is that that we find is that semi-classical calculations are subtle. And what we find, in fact, is that the entropy of the radiation keeps increasing. But if you look at the system entropy, then actually it follows the Page curve. Okay, so this is one motivation of our work. The other motivation is that, entanglement is one of the most important measures of quantumness. One way of looking at this is that entangled states violate Bell's inequality. And so usually entanglement is described for like coupled qubits and so on. But understanding it in many body systems is an open, interesting problem. And even understanding it in like this non-interacting fermions, you'll find that there are a lot of surprises. Okay, it's quite non-trivial even for like a non-interacting gas. Okay, so let me explain the model. There's some equations and so on, but it's really very simple. So it's so earlier I showed the free expansion in a tube. This is essentially the same problem with the difference that we are doing it in one dimension because it's analytically tractable. And the other difference is that it's an, so this is what I will call the system, and then it's connected to an infinite reservoir. Okay. And initially what we have is, okay, so this is a lattice. And it's described by this what's known as a tight binding Hamiltonian. So fermions can just hop on this lattice with some hopping amplitude g. So this hopping amplitude is the same everywhere, and then between the system and the reservoir, okay, there's something called a defect. Okay, so defect is just that the hopping element is different, or I have some on-site potentials or something. Okay, and initially I fill this system with it's completely filled, let's say, and it's in a pure state. And then, so it's like particles in a box, and then I open, so it's initially closed, and I open open a valve, and the gas escapes. Okay. Okay, so these defects are important because they help in kind of, as we'll see, they help in generating entanglement in the system. Okay, so so the analogy is that the system is like a black hole, and it's basically as the particles go out, they form the radiation. Okay, so that's the analogy, and we calculate the entanglement between the particles remaining in this box and those who have escaped. That's the entanglement that we'll compute. Okay, so now it's clear that at time 0, because it's in the system is in a pure state, there's nothing in the environment, and environment is completely empty. So it's they're completely unentangled, right? There's nothing in the environment, so it's completely unentangled. At infinite time, what we expect is that all the gas should escape to the environment, and so the entanglement again should vanish, right? So it's clear that this model will show something like a Page curve where the entanglement initially increases because things are because the particles are leaking, and they are somehow entangled with those remaining in the system. Okay, and eventually it's going to go to vanish. And we want to understand the form of this Page curve. Okay, so again, this is the model. So the initial condition, what I said is it's a fully filled system. So there is a particle at every site, and the bath is empty. Equivalently, you can just think that like you have energy levels in the system and they're all completely filled. Okay, so the spectrum in this lattice model is just in the energy of the at momentum k is given by minus cos k. So this would in a continuum, this would just be k square. So the initial state is a pure state and corresponds to 1 at 0 temperature and 0 thermodynamic entropy. And what is important is that the state we are constructing, it's like a Slater determinant, and it's in some sense a Gaussian state, in the sense that if you compute any correlation, all higher order correlations are given in terms of 2-point correlations. Okay, so this is what is defined as a Gaussian state. Now, Gaussian states are good because you can do a lot of calculations analytically. So one thing you can do is, if you look at this correlation matrix, so what is the correlation between particle creation at site I and a particle being destroyed at site J, when the system is in state site T. So this is the correlation matrix. It's a very important object. And its evolution is just given by this simple unitary dynamics. Okay, and then from this correlation matrix, you can compute things like, so initially, if you look at the, the simplest question you can ask is like, what is the density profile of the gas as it escapes, right? So initially, it's full, it's like what is known as a domain wall initial condition. Everything in the system is filled, everything empty, so it looks like that. After that, something escapes, so it keeps changing. And the observable that will tell us how the density evolves is just the diagonal elements of this density matrix. Right. So you can ask various questions like at time t, how many particles are remaining in the box, how many particles have escaped, and what is the current that's going, if you just look at the point between the system and the reservoir, what is the current at that point. What are the number fluctuations? Like if n number of particles have escaped, there will be fluctuations in this number. What are the fluctuations? So all these things you can compute just from this correlation matrix. Okay, so this has information about a lot of stuff. And for this particular case of, we are considering this Gaussian initial states, it turns out that the correlation matrix also has information on the entanglement entropy. Okay, so in general, entanglement entropy is difficult to compute, but for this class of initial conditions, you can compute it using a very simple formula, which I'll just say briefly. Okay, so the how much time do we have? 10 minutes. Okay, so sorry. Okay, I'll try to. Yeah. Okay, now for Gaussian states, the way to compute entanglement is like you look at the correlation matrix in the system and you just find its eigenvalues, and then the entanglement is given by some formula like this. Okay, so you can see it looks very similar to like what you'd get like the entropy of an ideal gas, right? Looks pretty much like this, but now it's given in terms of the eigenvalues of the correlation matrix. Okay, so this is a very nice formula which you can implement numerically and see how the entropy changes. The other way we do is hydrodynamics, and I'll tell you what the idea is. So the idea of hydrodynamics is that you think of it's a gas of particles, and so it's, in some sense, this is more like a Boltzmann equation. You can think of the particles at a semi-classical level. They have position and momentum, and you can ask what is the phase space density in position and momentum. Okay, so this is given by this object which I call n of xk. Okay, so this is the phase space density, single particle phase space density, and it has a simple Boltzmann equation evolution. Okay. And this object is actually related to something called a Wigner function, which can be given the wave function of the full system. One can compute this Wigner function, and from the Wigner function, if you do some coarse graining, it gives this phase space density. Okay, so now, basically we have to solve this equation, and this gives us the phase space density, and you have to solve this equation with some boundary conditions. There is some scattering at the defect, and there's some boundary walls and so on. Okay, so in phase space, you can see how the phase space density, which is initially it was like a fully filled Fermi sea on the left hand side. So this is space and this is momentum. So initial distribution looks like that, and this evolves with time in some way, right? And okay, so now the question is, how do you, given this phase space density, how do you compute entanglement entropy? And okay, so maybe I will. So this is just the derivation of the generalized hydrodynamics, which I'll skip. But okay, so now I'll just talk about the how do you compute entanglement entropy from this phase space density. Okay, so the idea is to use this formula, which basically again looks like so the idea is that I mean your system is in a non-equilibrium, it's not in an equilibrium state, but what you can imagine is that locally it's in equilibrium, and at a local level it's the entropy is just given by usual Fermi, if you assume a Fermi distribution at a local level, then you can compute the entropy, and that's the formula for entropy at a local level. Okay, and then you just imagine that there's a different local equilibrium at different points in space, and you integrate over all space. Okay, so that's done here. Okay, so this is the local entropy at a given site. And then if you want the entropy of the system, which is the left half, I call S of A, then you integrate from in the side of the system, and this is the entropy of the radiation. Okay, so you, using this formalism, you can calculate both the entropy of the system and of the radiation. Okay, so this is how we use hydrodynamics to calculate these entropies. Okay, so now somehow we can solve these equations. I won't go into the details. I mean, so basically we have to solve this equation with, so if there was no boundaries, no defects, then the solution is very simple. It's a solution of a Liouville equation. But once you put boundary conditions, then you have to take into account multiple reflections and so on, and then you have some solution like this. Okay, but now let me just show the what results you get. Okay, so you can compute everything from just numerically using exact microscopics, and you can compute things from hydrodynamics. And here I show compare the results. Okay, so this is for the density profile. So initially the gas is completely filled. It looks like the step function. And so it's 1 and then 0 everywhere. Okay, then at a little while later some particles have left, and so it changes the profile, and this keeps happening. And here I plot both the hydrodynamic results and the simulation results, and you'll find that there's perfect agreement between the two. Okay, and this is the current. Again, there's very good agreement. So one thing you notice is that so as this is the current as a function of time, till some time the current remains completely constant, and then it starts decaying. Okay, so the reason is that you have a finite system, and the current is a non-interacting system, so particles are just escaping. But at sometimes it realizes that it's a finite system, so this time is of order like the size of the system divided by the typical velocities. After that time, it realizes it's a finite system, and then the current keeps going down. Okay. Okay, so that's how the current looks, and again there's perfect agreement between hydrodynamics and numerics. Okay, and finally this is the entanglement. Okay, so now here what I plot is one is the entanglement entropy of the reservoir, which is the radiation. This is the yellow triangles, and that you can see is like the Hawking's calculation. It keeps increasing with time. Okay, on the other hand, if you calculate the system's entropy, that increases and then goes down. And then I also plot the exact microscopic entanglement entropy, which also increases and goes down. Okay, so it agrees completely with this system entropy. On the other hand, the radiation entropy from hydrodynamics is completely wrong. Okay, so okay, so this is the sort of interesting point, that there's remarkable agreement between microscopic entanglement entropy and hydrodynamic system entropy at almost all times, short times, long times, while the radiation entropy is very different. Okay, there are other interesting things like there's a power law decay out here, there's linear growth here, and we can predict this completely from hydrodynamics. Okay, so even the prefactors, everything can be predicted completely from hydrodynamics. Okay, so maybe I'll just talk about one last thing. I mean, entanglement entropy is something which is very difficult to measure in experiments. For this non-interacting fermions, there's a really amazing relation that exists between entanglement entropy and the number fluctuations. Okay, so I said earlier that you can look at how many particles have escaped into the environment. Okay, and then you can look at the fluctuations in this number. So it turns out that if this number fluctuation is something called full counting statistics, there's an exact formula which relates this entanglement entropy to the full counting statistics. And there's this famous paper of Click and Levitov which says that quantum noise can be used as an entanglement meter. Okay. So in our work, what we find is that even in this simple system, if you look at just the number fluctuations, so I plot number fluctuations versus time, that also has this page form. And in fact, they agree, I mean, if you just, even numerically, they agree extremely well with the number fluctuations and entanglement. Okay, so you can use number fluctuations to compute the degree of entanglement between two quantum systems. I think this is not completely understood, like is this generally true? There's a lot of open questions. Okay, so I think I can now wind up. Okay, so this is what we tried to explain, that in this simple model, you capture some features of this black hole information paradox. Our simple model of a freely expanding Fermi gas, and where we compute the entanglement between what's remaining in the box versus the what's radiating. That captures has the same form as the page curve. And what's nice is that you can compute many things analytically, that like the exact time dependence at short times, long times, and so on. This is another very interesting aspect that it's kind of not clear why exactly this is just an observation at the moment, not clear why exactly this happens, that the bath entropy agrees completely at early times, but at late times it deviates from the system entropy. Okay. So note that the entanglement entropy, in principle, the system and path will have exactly the same entropy. Okay, so that's an exact result. So there's some open interesting problems are like trying to understand finite temperature states. I looked at the ground state evolution, but you can ask finite temperature states, the effect of interactions. And I looked at fermions, but looking at bosons is also an open and interesting problem. Thanks.
Thank you. Zahid?
A very beautiful talk. I have on the free fermion lattice, I mean, on the 1D lattice you showed, have you considered adding interaction and see whether in the entanglement spectrum has any discrete evolution or abruptive evolution? Have you considered adding interactions?
Right, yeah. So that's something we are doing currently, we have added, like with interactions, how does it change? And the qualitative features are almost the same. So of course,
I see. So you don't expect any abrupt change in the entanglement spectrum? I'm a bit surprised if you...
No, qualitatively it looks the same.
Oh, really? I see.
Interactions right now, of course, once you add interactions...
Go closer to the mic.
Once you add interactions, it's mostly numerics. And even with the best techniques, we can do like quite small system sizes. So it's possible that when you go to thermodynamic limits, things can be very...
Right, actually I was thinking of in the lattice, in the thermodynamic limit.
Right, yeah. So that's of course very hard. But at least our preliminary results seem to say that it's more or less the structure same. Some details change, like the power laws and so on, they change, but the quantitative features are the same.
I see. Thank you.
Can I ask one or two questions? I'm here.
Yeah.
Thank you. About this curve where you are showing the Hawking prediction and the prediction by Page, to me it is a bit strange because the effect of entanglement, which is decreasing the entropy as I understand it, So that is only, I can see it after a certain interval. Because initially the Hawking line and the page line, they look very similar. So I think this is a very important question. Why the entanglement is not setting from the outset?
Why the entanglement is
Not there after a certain, I cannot say the parameter. Is it time?
this is this is time.
Yeah. So only after a certain period we can see the effect of the entanglement. But the entanglement, as I understand, whatever be its extent, it should be from the beginning. Why it's not in the beginning?
No, see, initially, of course, they are unentangled, right? Because our starting state was it's unentangled.
But once you open,
then it starts. The particles start escaping, and the system and the reservoir are getting entangled. So that's fine. After that, the radiation, the entropy keeps increasing, right? Now somehow you're not able to keep track of the fact that there's also an entangled pair in the black hole. Okay, so even though, every time, I think the mechanism is like at the surface, you create entangled pairs, one goes inside and one goes outside. Okay, and that's why the entangle builds up. But at the end, somehow you are left with nothing in the
okay, so basically my point was it looks like there is an onset of entanglement. The curve looks like that.
Okay, at this point there is, the interesting question is why at this point they start deleting.
Yeah.
Right?
So my second question is, and this is very simple. If you look at a black hole, and what would be the signature of this entanglement? If you think in terms of conducting an experiment, what would be different if you look at the black hole, where the pure state persists and where there is this entanglement? Because ultimately, to differentiate between the two pictures, we need to find some way of confirming it.
So I think, okay, I know nothing about black holes, like I said. My understanding is that, what is perhaps missing is that the radiation that's coming out is not completely uncorrelated. So the correlations are carried in the radiation.
So Hawking's prediction is it's completely black body radiation.
Right, yeah,
there is nothing else.
Yeah.
Thank you.
Yeah, I think that's,
or more.
Professor Hoodbhoy, I have got a very basic question. Will you please explain the phenomenon of entanglement? This is very, this is from fraud engineer, yeah?
Your mic is off.
I think it's okay, yeah. Okay, so I think it's simplest way to understand entanglement is maybe just if you think of a pair of qubits or pair of spins, right? And if you create them in let's say a singlet state, up, down, minus, down, up, okay, then it's an entangled state in the sense that you can't write it as a product of two states. Okay, like if unentangled state is like you have up, up or up, down. That's unentangled because it's a direct product. But up, down, minus, down, up, you can't write as a direct product. That's a mathematical definition. Practically, what it means is that if you take an entangled state and of two spins, and you take one spin, and the famous example is Alice takes one and Bob takes the other, and you do experiments, then what you can measure in any direction a spin here, and you know exactly what Bob will Alice makes some measurement, and then it's exactly determined what Bob's measurement will yield. Okay, so in that sense, their measurements are completely entangled. So this is, a very rough explanation. Like I said, I think the cleanest way to understand entanglement is in terms of Bell's inequalities. Entangled states can violate Bell's inequality, and so are really measured quantum. quantum correlations. I mean, of course, like if you have two up spins, if you measure this and you can also get up here, but that's like classical correlation. But quantumness is really in the fact that you have a lot of choices in what you measure and so on. So it's a bit involved, but that's roughly the idea.
And what is a curve, a Page curve?
Page curve is the evolution of entanglement with time, entanglement between the black hole and the radiation that it's emitting. Right? Just like I looked at entanglement between two spins, now I can look at entanglement of the black hole and the radiation. And like how does it evolve with time? That's what the Page curve is.
Straight. Okay, thank you.
We were to have 3 talks in this session, but we've run out of time. The third talk will be after lunch. So if there are no further questions, then let's thank there is one further question.
Unfortunately, I have never seen a wave function being used to describe a black hole. Usually it's the metric that we use.
Usually it's a
Metric for the black hole. But you have mentioned that wave functions are being used to describe a black hole. Could you please elaborate on that?
Okay, I don't like, of course, writing a wave function is very difficult, but I'm saying in principle, if we believe quantum mechanics describes everything, we should be able to write a wave function, right?
Yeah.
So I'm just saying in principle, of course, writing in practice, because I mean, even the quantum theories, but I think in string theory, maybe there's ways to write, in some sense, a wave function for a black hole.
Well, you can only write down a wave function if you know what the degrees of freedom are. We don't know that for a black hole.
Right, yeah. But I think string theory, there are models to describe the microscopic degrees. I maybe say, I don't know, Ashok.
Okay, thanks very much. And let's all go for lunch.